Hello, this is Tai here from Alex. Welcome to the CANplus tutorial. CANplus is the CAN bus feature package of the VEConfig service tool for the RLX vector-powered devices. In this tutorial, I'm going to show how to handle two common scenarios that are related to the CAN bus. One is how to limit CAN bus load and work on busy CAN buses. The other scenario is how to send and receive data on the CAN bus. Let's start with the CAN bus load first. If the bus load is high on a CAN bus, telegram delivery may be delayed. In the worst case, telegrams may not be sent at all if the CAN bus is busy with higher prioritized messages. Normally, VEConfig uses the entire available data throughput. The CAN identifiers used are in the range of 580 to 680 in hexadecimal, so identifiers larger than 580s may get delayed. This is because of the arbitration of the CAN bus that prioritizes telegrams with lower CAN identifiers. If this is a problem, we have the CAN busload limitation feature in VEConfig that reduces the CAN bus load. For example, in the CAN bus page, we can see the CAN bus load in the load box here. The busload by VEConfig box here says how much of the CAN bus load is caused by VEConfig. That is the bus load we can limit with the limit feature below. For example, if you start an operation that uses high data volume on the CAN bus, we can see the bus load rises to about 50%. If you now limit the bus load to, for example, 20% and restart the operation again, we can see the bus load rises, but it's limited to the 20% we put in the limit feature. We can also see the operation is slower now, but the limit is kept. If you release the limit again, restart the operation, it goes fast again, and the full bus load is used again. Next thing I want to show is sending and receiving data on the CAN bus. For this, I use the CAN open screen on the left side. A common situation is that some values should be provided on the CAN bus. For example, this may be the actual values like torque or speed of a vector-powered device, so the vehicle controller can read them. To realize this, I use the so-called transmit PDOs. These transmit PDOs define up to 12 adjustable telegrams that can either be sent on demand or cyclically from the vector power. I want to start with an example and send some values cyclically on the CAN bus. For this, we use the first transmit PDO and add some data on the telegram. Let's take this control mode. Pick the first. We have an integer value that has a size of 32 bits. And add some booleans. These are two booleans with 1 bit each. So we have a telegram size of 34 bits in total. So the data is defined now. We have to check the other values of the telegram. That is the telegram identifier. This is 181 in hex. We have a transmission type. I take cycle time here, so the telegram should be sent cyclically. And I put a cycle time of, for example, 120 milliseconds here. So now the telegram is set up, and I can switch the CAN open stack to an operational state, and the telegram should now be sent. Let's have a look in the CAN message monitor. So we have here our telegram. We have a size of 5 bytes, which is from the 34 bits. And we can see the one here. This is our control mode. Speed is 1. And we have these 2 bits on the end, which are toggling. If you keep this window and I switch the control mode, we can see the message that represents the value here. I can switch back to speed mode. So another feature we can use is the extended frame telegrams. So we can send 29-bit identifiers. For this, I switch back to pre-operational state with the stack. So the stack stops sending, and I take a message number that's an extended frame with a higher number, and go back to operational state. And again, have a look in the CANplus. So we have now an extended frame with the same data here. After we successfully send CAN messages, the next task will be to receive CAN messages on the CAN bus. I want to show you an example where the control mode is changed over the CAN bus. To receive CAN messages, the receive PDOs are used. I again pick the first receive PDO and put the control mode to the data. Again, we have the identifier here, which is 201. I can change this if I want. Take a standard frame, switch back the operational state to pre-operational to commit these changes, and switch back to operational. Let's take again our CAN monitor. I prepared two messages on the identifiers 201, and I can send them while double-clicking. And if I do that, the control mode switches here from talk to speed, back to talk, speed. So this is sending. Please note that the extended frame feature is only available on new Vector embedded firmware versions. If you need this feature, please contact Alex to have maybe a newer version, if not available on your device yet. The other operations on this page are saving and loading the configuration to the database. With this, I can save the Telegram configuration and get back to this later. I can also use this to switch between different configurations. The export feature saves the configuration as a DBC file. This is a common file format used in many other CAN tools. At last, if you want to make this configuration a permanent setup, please make sure you have assigned a node ID at the top. Set the initial state to operational and save the configuration to the device. The features shown in this tutorial are included in the CANplus add-on. This add-on has to be licensed via the licensing manager. If not done yet, the licensing manager is available via the Help Licensing Manager menu. Please notice there is a 7 days trial license available when licensing the first time. The trial licensee is free of charge. That's all for this time. We have seen how to send and receive data on the CAN with the RDX vector powered devices. We have also seen how to work on a heavily loaded CAN bus. I hope this information was useful. If you have any questions or comments, feel free to use the feedback feature in the Help menu. Thanks for watching.